Hi, my name is Charlie Berger. I'm the Senior Director of Product Management for Machine Learning, AI, and Cognitive Analytics at Oracle. And this presentation is all about the changing role of the DBA. With the Oracle Autonomous Database, many things that DBAs have done in the past and database developers have done in the past are becoming more and more automated. And this opens up a huge opportunity, I think, for those technical individuals to take their valuable skills further. And I believe that you can go from database developer to data scientist in 6 weeks. And I'll try to share with you why I believe that and how to go about starting down this journey yourself. Oracle has a safe harbor requirement to always talk about any futures that I may mention that under legal obligations we have to just have put up this disclaimer. And the goal of this presentation is to share an attainable, logical, evolutionary path for Oracle technical professionals to add machine learning to their valuable Oracle data skills to extract more information, insights, and to make predictions. So let's get on with the presentation. If you like, you can follow me on Twitter. I'm Charlie Datamind. Please follow me if you have a chance. And I'd like to start at the top, right? What is Oracle's mission? Oracle's mission is to manage and protect the world's data for the benefit of all. Now, data is the center of everything, and it's certainly the center of machine learning algorithms that require data to sort of look through that data, find patterns, find and discover insights, and build predictive models that can be used to make predictions. And it requires data, but it's also part of a larger ecosystem that includes other infrastructure and other applications. The applications part of this is interesting because as a database developer, you want to serve up information into applications, but you can also serve up more enriched information with insights and discoveries and predictions that you're able to make using the machine learning that comes embedded now in the Oracle database. So it's a fascinating sandbox in which to play. So today, many DBAs spend a lot of time on maintenance and not enough time on innovation. So a lot of the budget is spent on maintenance, on security, and reliability. And with the autonomous database, without going into all those details, because others at Oracle can go into that in much greater detail than I can. But the goal there is to help with this and to automate this, almost as Larry Ellison would say, as driverless cars automate the tedium of some driver driving you from here to there. So with all this change, how will the autonomous database change things? How can you expand your DBA and your database developer and your BI analyst, all your SQL skills? How can you expand your skills, add some new skill sets, and become a data scientist? Well, let's go over it. The Oracle Autonomous Database has some very key features, right? It's self-driving, it's self-securing, it's self-repairing, it has all these patches that come in. I use it myself and it's a breeze, right? I can open up a new cloud account. I can, as I said at Oracle Open World, riding up the escalators, I signed up for my new Oracle Cloud account. And by the time I got to the top, I had a link and I was ready to go. So a lot of the work that might have to have otherwise been done by a DBA, it's a little bit more of a self-service or a DBA or whoever, but setting it up and then setting up the users and all that is and patching and all of that and monitoring is done automatically with the Oracle Autonomous Database. And so many of the different tasks of database infrastructure, detection and recovery of failed or sick servers, hang management, anomaly detection, query optimizer, all of the indexing, all of that is automated. And again, there are other people at Oracle can talk in much greater detail and authority on these topics than I can. But so I'm taking it from the faith of, well, these things are being done for you. What are you going to do with all your spare time? Well, typically, DBAs are responsible for a number of different tasks: maintenance tasks, tuning of the systems, database provisioning, patching, database optimization, and they don't have enough time to work on architecture planning, data modeling, and in fact, more innovative kind of things. So with the autonomous database doing many of the mundane maintenance kind of tasks, then you can move further up the innovation scale because those things are done for you. So now, if the database is running smoothly along, then you could say, well, I have all this data. How can I help? And I think that the database developers and DBAs and business analysts are already doing many of these things. They're already the data engineer who's doing the architecture, but also a lot of data wrangling, dealing with a lot of security, dealing with application tuning. But But I contend that the open door, the door that's been opened for these very valuable, with all their technical and data skills, the new door is machine learning. Because machine learning is, its goal is to try and automate a task. It's not like you have to have a PhD in statistics to know which statistical test is the most appropriate given the distribution of this data. It's machine learning, right? Machine learning says, give me a set of data, tell me essentially what kind of task you're trying to do, and go. Now, there's a lot more to it, and I'll cover that in the rest of the presentation. But I think with your data skills as a Oracle technical professional, you are in a very advantageous position to be able to move forward, and it's not that hard. So what can I do to prepare for this evolution? And I call it an evolution, not a revolution, because I think you'll find that you're probably doing a lot of this work already. So are you ready to make this journey? And I think you probably are, because you're probably already doing most of the work. Now, a data scientist, and I consider myself a data scientist, and I think these days anyone that takes a quick Coursera course or does a little bit of work is always calling themselves a data scientist. But if you look at it, a lot of times the real work that's going on is, hey, I'm, as a data scientist, I want to solve a problem. I want to figure which customers are likely to buy a hybrid car, right, or which customers are likely to have a medical claim that's maybe non-compliant or something, or what's my next best offer from market basket kind of analysis. And so the first thing the data scientist does is he goes back to the source of the data. Where's that data? Oftentimes it's in an Oracle database. And they say, hey, I need some data. Can you give me this data? So that you, the database developer, the data DBA or the BI analyst, has to go fetch that data. And they'll say, well, can you give me age? I need to know the person's age. And you'll say, well, I have their birth date. I can compute that for you. And the data scientist says, yes, thank you. I need another variable. I need to know, have they had any dropped calls? Well, there's some functionality in the database called SQL patterns and SQL windowing functions and such, where you can use to compute things like that and count events. And so what you find is the data scientist is either saying, give me the data, I'll take it out of the database over here into Python or R or Watson or SPSS or SAS or some other land, but oftentimes Python or R. They're saying, give me the raw data and I'll do all my analysis and all my data preparation, data transformations over here. Or more often than not, they are asking the database developer to do the data extraction, the data wrangling, deriving all these new attributes, like what's the rate of change with this variable, count how many times the temperature gauge went above 32 degrees, count the ratio of this and that. There's a lot of SQL windowing functions for the number of checks that are written most recently versus the longer term average. There's a lot of domain knowledge that is associated with good, proper machine learning, and someone has to do that. And my contention is you're probably doing that a lot already. I have various customer examples I can point to where the DBA or the database developer was already doing that. And then at this magical point, somewhere in that process, is where the machine learning happens, right? That the data has been wrangled, it's been joined with other data. You finally have this nice, well-behaved set of data with a nicely behaved target field, like did they churn or not? Did they commit a crime or not? And all that data is something that maybe you've done, and it's 80% of the work. And then the database, the data scientist then, I don't mean to simplify it, but being a data scientist, it seems kind of cheating. I press a button and say, go. And now the machine learning algorithms walk through all that data and it finds the patterns, whether or not it's using a random forest or a support vector machine or an XGBoost algorithm, which is coming in the next release of the database, or a neural network or a support vector, any of the different generalized linear model, or all the above, because it's so easy to do inside the database. But at some point, I press go and the algorithms walk over that data and find a pattern. I can measure how accurate that model is because I also, as a data scientist, know to have a holdout sample. Now, this is one of the little tricks that I think as a database developer, maybe you didn't know, but in order to build a model and then validate it, you have to have a randomly selected sample of data to build the model on, and then a holdout sample of data that you already know the outcomes. So you apply the model, the predictive model that you created, you apply that to the holdout sample and you make predictions about the past. You can say, aha, this model is 88% accurate because it makes these predictions, and 88% of the time it gets them right. So then at the end of all that, the data scientist will say, hey, I've got this really good model. I'm going to use this model to make predictions, or what they call scoring the model. I need more data. So can you, Mr. DBA or database developer, can you send more of the data over here? So over in Python land or R land or some other analytical platform. I can use my predictive model to score things, and then at the end, I need you to import the results. And sometimes they say, well, here's this predictive model I've created. Could you please import it or take the logic of it and somehow operationalize that? And there's an interesting study that came out recently saying that 87% of all big data science projects fail. They fail to go to production. They fail to be implemented, like the Netflix challenge. That was an interesting challenge a few years ago to get a more accurate predictive model for movies. Someone came close. They gave them the $1 million, but the rest of the story was Netflix never implemented that. Why? Because the methodology was this convoluted methodology that happened outside of the database, and they found that it just was too much trouble to try and implement that. And if you do all of this inside of the Oracle database using the embedded algorithms that come with the Autonomous or the Oracle Database Enterprise Edition, with the advanced analytics option on premise or in the extreme and high performance editions on the database as a cloud service, then all these algorithms and the scripts are running inside the database. When you build a model, it's happening inside the database. When you apply the model, it's happening inside of the database, and it's very easy then to automate that, schedule that, or just call a SQL function to ask for a real-time score of this new record, and or score a whole batch of things, or even better, embed it in an application. So my contention is you're already doing most of this work today. It's just that little bit in the middle where the magic machine learning happens, and I want to kind of show you, kind of like Penn and Teller, sort of peel back the curtains here a little bit, pull them back, and show you what's going on there. So in machine learning, there's a very well-accepted common methodology. It's called CRISP-DM. I think it stands for Cross Industry Reference Mining Model, process, something like that. But it's basically sort of just the basics, right? It says before you start on some sort of journey, you need to understand what the business problem is. What's the business understanding? In my example, I was trying to figure out, well, which customers are likely to buy hybrid cars? Because I'm Toyota or Ford, and I want to do a campaign to try and find people who are likely to buy hybrid cars, not gas guzzlers, not trucks. I want to sell, small electric cars, and I want to approach the right people because it's expensive to drop leaflets from airplanes to contact everyone. So I want to be careful about who I send my limited marketing budget towards to try and attract those people. So I need to understand the business. I also need to understand the data. What kind of data do I have? Well, I have who bought a car before. Maybe I buy some data and I have what the average income, the number of children that you have, your education level, what your income level is. Have you ever purchased a hybrid car before? Has anyone in your family ever purchased a hybrid car? Have you ever rented a hybrid car? So the more data I can get my hands on that either you own or you acquire or you assemble, the better. Now, I think both of those areas are something that a database developer, a BI analyst, or a DBA would know those skill, know that information. They know their business, they know their data. The next part is the data preparation. We talked about that a little bit earlier. That's where you say, if I could, like they say, hey, could I buy a vowel? I want to buy another variable. So wouldn't it be nice in this who's going to buy a hybrid car to have this variable that says, have you ever bought a hybrid car before? I'd be willing to go out and buy that variable or assemble it or take a little bit of effort to do it. And maybe I can get it. Maybe how many cars have they ever bought from me in the past? So maybe as a DBA or a database developer, I can go back upstream, find that data, compute that attribute. What we would call, in the data science land, we'd call that an engineered feature, right? And what we do is we keep on thinking about, kind of scratching our head and saying, if I could get the best variables that would help me make a prediction as to who's going to buy a hybrid car or not, which variables would I go after? And do you live in New England? What's the average weather? Because sometimes hybrid cars with electric motors don't do well in the very, very cold weather. So you have all these hypotheses about what are the variables, and you want to go get as many of those variables as you can, those attributes in the database, and assemble them and bring them together. Still, that's the purview of a database developer, right? That's not necessarily limited to a data scientist. Now, the data scientist may ask you to do it, or they may say, give me the data and I'll do that kind of work over here in Python. And there lies one of the problems about how do I then operationalize that bit of Python or R code. So that's a whole nother can of worms there. Then there's the modeling. Well, let's get into that. You have to know which type of category of algorithms you want to apply, whether that's regression or classification or clustering. Then there's a certain amount of evaluating the models. Is this a good test? And we talked about the holdout sample before. And at the very end, you do the deployment. So I contend if you kind of like if you're learning how to ski, learning how to play the guitar, or just sort of learning how to do data science, that you kind of focused on each one of these things for about a week, which is not that much time. I mean, you could do it in less time, I contend, but if we just kind of take a look at these things and focus on each one of them for a little bit of time, I think we'll, at the end of this period, get you up to be a data scientist. So let's take a look at a little bit deeper. And then at the end of this, you are in fact the data scientist, the sexiest job on the planet. They say, you add an extra $100,000 to your income, who knows what, but it's a fun place to be actually. So I did want to go off on a tangent here for just a minute. That when people talk about data science or machine learning, they often talks about, or analytics in general, they often talks about this analytic maturity model. They talk about what happened, why did it happen, what will happen in the future. And this what will happen in the future using clustering or classification or regression techniques is what a lot of people think is the be all end all. We're done. Well, from our point of view, we're not done there because it's not a solution unless you've now automated this. You need to then run the script over and over every day, every week, in real time. When something happens, when you submit your expenses, it should give you a pop-up window. Are you sure this is right, Charlie? It seems awfully high. Or when you check into a hospital, maybe they have an alarm that goes off. Uh-oh, this person is likely to have a surgical readmission. Let's keep an eye on this patient. Same thing with any domain problem that works for you in your particular world. And it's that automation of things, I think, was where Oracle differentiates itself from everyone else, because we didn't choose to move the data to another platform. We said data is big, algorithms are small. Doesn't it make more sense to move the algorithms to the data than the other way around? And that's what we've done. And when you do that, it opens up a lot of opportunities. So we now have a family of offerings. We've been working on this for, close to 20 years now, I think. When I and a bunch of us came to Oracle from a company called Thinking Machines, and we had fantastic, massively parallel processing algorithms that ran outside the database on special servers or commodity hardware, but you had to move the data somewhere else. This is what I'd almost call legacy machine learning, which is what a lot of people still do today with Python, R, or whatever. What Oracle did was we moved the algorithms to the database. We taught the database how to do math. So we have a bunch of PhDs in machine learning. We taught the database how to do, neural networks, decision trees, and so on. And we exposed those algorithms via SQL, what's called Oracle Machine Learning for SQL. You may also know it as Oracle Advanced Analytics or Oracle Data Mining. It's the SQL API to the algorithms. We also wrap and expose those algorithms to R. That's called the Oracle Machine Learning for R. We're coming out with very soon, in early 2020, Oracle Machine Learning for Python. So those same 30-something algorithms that we have can now be called via the Python language. We wrap and expose them to Zeppelin notebooks. We wrap and expose them and put a real nice GUI on them called Oracle Data Miner. It's a module or an add-in to SQL Developer. We have algorithms that run outside the database, Oracle Machine Learning for Spark, and then we've added this new thing called Oracle Machine Learning Microservices that help with the deployment and operationalizing of models, and that's also coming soon, I guess is what I'd say on that. So why does machine learning fail? Well, there's a few different, and how can you help with this? There's a few things that happens. The analytics and data science teams, they usually work outside of IT, right? They see IT as an obstacle. They're resistant to new approaches. They want their own space. The IT, the infrastructure team, they're happy to stand up dedicated commodity infrastructure, and they don't generally like Oracle or Exadata. They kind of want to stand up something quickly. The database administrators, well, they're the guardians of the enterprise data. They want to do more with the Oracle database. So these guys all have sort of different opposing points of view. And the business or the process owners, they just want better outcomes. They want them faster. They want them for less money. So I think we can help. Now, this is also sort of fuel to the fire of why, what I'm trying to articulate, why it makes sense for you to evolve towards becoming a data scientist, why this all makes sense. Fern Halper, a very smart woman at the Data Warehousing Institute, asked this very important question. How long does it take to put a defined model into operational use? Now, the defined model is the key part of this question. It says, okay, I'm a data scientist. I've already built a model. I've got a 92% accurate model for who's going to buy a hybrid car. I want to operationalize that. I want to put it into production so all the other people on their dashboards using Oracle Analytics Cloud or an ERP or call centers, they all have these predictions pop up in their dashboards, their applications. How long does it take for that to happen? Well, if you look at that, from 3 months to 9 months, I think it's about 65% of the population, and 9+ months also means never, right? So this is an awfully, awfully long time. And I look at this, and now this is Fern's study. This is my Charlie Berger editorial comment. Well, they must be using tools like that, right? Because I can't imagine why it would take that long. We've moved the algorithms to the data management platform. So if they're using us, it'll be immediate, right? I build a model, I apply the model. Build a model, apply a model. It's a script, right? It's a SQL script. Very soon it'll be a Python script or maybe an R script in the autonomous database. So right now that's all SQL, pure SQL, and I'll show you how we do that. So as I said earlier, we've decided to move the algorithms, not the data. So what you're looking at the right is something called the naive Bayes algorithm. It's basically counting and developing conditional probabilities. How many times did the person buy a hybrid car and they were a male? How many times did they buy a hybrid car and they were a female? How many times did they buy a hybrid car and they were a renter, or they owned a home, or they were a cat lover or a dog lover? And when I get to numerical values, like income or age, what do? I bin that. I bucketize that into like 10 deciles. And I say, how many times did they buy a hybrid car and their age was in bin 3? And when I get to things like text, unstructured data, I use Oracle Text under the hood to tokenize that. And I say, how many times did they buy a hybrid car and they use the word guzzler, like gas guzzler, or they use the word gasoline, or they use the word expensive, or whatever. So I have a lot of other capabilities in the database. I bring that very simple counting algorithm into the database. So you can imagine that's a very achievable, possible algorithm to put inside the database. And we did that almost 20 years ago, right? So since then, every major release of the database, we've added 2 or 3 additional parallelized implementations of traditional and cutting edge algorithms, to the point where now we have over 30 algorithms for neural networks, decision trees, clustering. They're all enabled with the ability to mine text, the ability to mine aggregations, spatial and graph data, and it's all secure, it's all scalable, it's all encrypted data. All of the other features and functions of the database that you know so well are still there and still in play, and these models are actually in fact first-class objects. So when you do this, you've transformed the database into much more of an AI database, almost a thinking database. And when you think about this more and more, it really changes pretty much everything. It opens up a lot of new doors. These algorithms are fast. If you look at the generalized linear model over here, I can build a model in 600 million rows, 900 attributes in a minute. Okay, that is 512 degrees of parallelism. So this is a properly sized data warehouse, Exadata box. But incrementally, I'm adding on to that the algorithms. This does not, when you run the algorithms, the lights don't dim and the whole system crashes to its knees. Because we move the algorithms to the database, this is just a complex query. And this is faster and more efficient than exporting the data to some other platform, doing the math out there, and then importing the data back in again. And how do you do the predictions on new data? This is much more efficient and simpler architecture, and faster, of course. So today, Oracle is looking to manage and analyze all your data. So you may have data that runs outside of the database. We have a bunch of algorithms that run over there as well, the Oracle Machine Learning for Spark. We also have algorithms that run in the database and in the autonomous database. And they're all the same algorithms, the ones in the database and the autonomous database. They're the 30 algorithms I'll show you in a minute. And we expose those via a nice drag and drop GUI with Oracle SQL Developer. We expose them and wrap them and integrate with R. So you can use R to call them, or you can even do callouts to R. Very soon coming is the Python integration. And on the autonomous database, we added these new notebooks. So describing what we have for Oracle Machine Learning is becoming more and more challenging, because it keeps on kind of growing. There's like, what language do you speak? R, SQL, Python, Notebook, GUI, we have them all. And we also have Big Data SQL that sort of bridges the gap between these two worlds. And my own belief is that it's, again, your database administrator, database developer kind of skills that allow you to do all these engineered features. Using clever SQL, you can say, well, I'm going to take the data off the big data lake, and I want to boil it down to the number of counts. The number of counts I had a dropped call, the number of counts I had an event of the temperature gauge towing high. I want to measure the changes over time. So I join all this data together. And as I always say, if the centroid of all that joined data to solve a particular problem is anywhere close to the database, I would continue on and use the algorithms of the database, because that's where we have the most differentiated machine learning capabilities. In terms of analytical functions, our algorithms, we have, it's over 30, plus we integrate with R, and very soon we'll be integrating with Python. But if you want to do regression, which is the generalized linear models right here, is what 80% of or more of what most people do most of the time. today just because by regulations and things like that, banking, they sort of know that algorithm, they understand the transparency of it and the coefficients. We have that. We have ridge regression in there. We have linear models. We have support vector machines, linear and Gaussian models, random forest decision trees. Logistic regression is what I was talking about over here, rather than multivariate, regression where I'm fitting a numerical value. Here, I'm just on the classification. I'm doing, what's the outcome? A, B, C, 0, 1, yes, no. We have unsupervised learning techniques like clustering. We have anomaly detection where we train on what you tell us are normal records and we apply that to new records, and we flag things that we think are most dissimilar to the training population. So quite a rich portfolio or toolbox of algorithms, and these are not a separate toolbox. These are part of your Oracle database. And what's most interesting, they're part of the Oracle Autonomous database, which is now, as Larry Ellison announced at Oracle World, they're free, always free tier, includes the Autonomous database and all these algorithms. And if you, by the way, have unstructured data, transactional data, geospatial data, you want to build partitioned models, we sit within all the rest of the Oracle functionality to allow you to harness these capabilities. And oh, by the way, there's all these statistical functions too. Like most people don't know that I have like t-test, f-test, I have Pearson's correlation coefficients, all sort of basic statistical functions that have been in the database since 10GR2, but in combination with all the rest of the analytical SQL functions, SQL windowing functions, lead lag, all the algorithms, it transforms the database into a very analytically capable and very powerful platform. So my slides were just sort of jumping there. I'm gonna see if I can get through this again. So here are the SQL statistical functions. If I just want to do a statistical test of comparing the amount that men buy versus what women buy, I just do a SQL query, and you can see the code there. Very, very straightforward. I think this is going to jump on me, so it is. So I'm going to have to bring it back. If I want to do a classification model, I'm going to build a model to see who's likely to buy, let's say, travel insurance or some sort of insurance. Well, here I go. Build DBMS data mining create model, buy insurance. The type of model is classification. The target field is buy insurance, yes or no. The unique identifier is customer ID, and the data table name is customer insurance lifetime value. Once I build that model, I can apply the model in real time or in batch and get my prediction. Very, very straightforward. Most people that are using SQL and are SQL skilled look at that and they go, I can get it. I understand that. Makes sense. It's going to over jump on me here again. Let's go back. Now, if I want to do an attribute importance, there you go. It's the same sort of syntax, but now we're just finding what are the key variables that are most associated with something. So very straightforward. Let's bring it back once more. If I want to do that same attribute importance using R, well, it's just R syntax through the same function. So R syntax, I get the same results, 0.21, 61, and so on. Let's jump that back. Now, if I want to use Python, it's coming very soon in early 2020, I can use Python syntax and call the same functions. Now, in R and Python integrations, we also allow you to make callouts to run other Python and R packages. But in doing so, there is a trade-off, right? You say, I want to use this R or Python package, but the package is over here running in Python or R, and I have to take the data out of the database, move it over there, run the package, do the math, and either leave the results over there or bring them back. So there's a little bit of overhead. I consider that a little bit more like using analytical duct tape. And if you want to do that for 99% of what you want to do, that's not a good way to go, perhaps. But if you want to use it for 5 or 10% or 2%, just for those things that you need a special call out for some special package, go for it. It's what is one of the beauties of our integration with those other very powerful and flexible languages. But you want to probably try to use our in-database algorithms to get the full scalability and the performance. So going forward, where's the opportunity? Well, with the Autonomous database, we add these new Oracle machine learning notebooks. They're collaborative user interfaces. They support data scientists, data analysts, application developers. There's sharing. It's embedded in the Autonomous database, and we'll go through that in a little bit more detail. So let's talk about this 6-week journey. So let's start it. You're supposed to go from a cocoon to a butterfly there. Okay, so let's start this. So there's a process. We talked about that before: business understanding data preparation, and so on. Let's go through it. So the very first one, week 1, business understanding. These are the types of problems you're probably trying to solve. Your managers will say, or your president or somebody will say, can you predict employees that voluntarily churn? Can you predict customers that are likely to churn? Can you target the best customers? Who are my best customers? How can I combat fraud? Or the killer of them all, the last one. I've got all this data. Can you mine it and find some useful insights? Please avoid that at all costs. That's the worst way to go. So what you want to do in this very first week is you want to think about what Albert Einstein says here. He says, if I had a problem to solve and I had 55 minutes to think about it, I mean, if I had a problem to solve, I'd spend 55 minutes thinking about the problem definition. And once I get the problem definitions nailed down, I'd spend 5 minutes thinking about it. Like if I want to save the planet, do I mean save the planet, the men, women, and children, the trees, and the animals, or do I just mean save the planet, just the children, or just the trees, or just the fish? And whatever you come up with for that problem statement, it's going to change the way you approach the problem. So you really want to think about that. And if you look at this, predict employees that leave, target the best customers. Each one of these things on the left are very poorly defined. In the middle, they're much better defined. There's an explicit calculated attribute like, did you churn, yes or no? Which employees left, flag them as 0 ones. What's my definition of my best customers? Maybe it's whoever has spent more than $500 in the most recent 18 months, and so on. And each of these different types of problems will map into different types of machine learning techniques. Classification, usually, sometimes association rules, regression, anomaly detection at the bottom. So that's week one, right? And in the notebook, here's an example of that. Okay, I have my notebook, I have paragraphs, and in the paragraphs I can kind of describe what I'm doing. There's a situation here that Heather has spent most of her time in the past couple of years extracting and preparing data for analysis, and they have the situation where they're trying to find customers who are able to have good credit customers who can buy a flat screen TV or a large appliance and make the first payment, but continue making payments and not have to return it. So there's a number of customers in the past that have done this successfully, and we want to use that data to predict which customers we should proactively go after. So that's something that with your domain knowledge, of course, you know your domain knowledge. That comes natural is my argument. Week two is data understanding. Does the data, review the data, does it make sense? Are the number of liabilities in the fourth or fifth column, they're all making sense? Are the ages all positive values? Are the income values, do they all make sense? Are the genders male and female and whoever or whatever, loan amounts, do they all make sense? So take a look at the data. There's a little bit of data profiling, and here you can see what's happening. This paragraph here is SQL, so %SQL, select star from whatever. That's just typical SQL. So you're almost a data scientist here. Now here, you may want to use some of the Zeppelin Notebook's simple graphing capabilities. So here, once I have a table, I can graph it. So if I click on that little graph, it gives me a graph. And here we're looking for good credit customers. That's the variable. That's what we're targeting. So we flagged with our SQL skills. We created a column and we said if they fit this profile, we flagged them as good credit. Otherwise, we call the other ones other credit rather than bad credit. We call them other credit. We're up to week 3 already. So week 3, data preparation. Remember, you have date of birth, but I, as a data scientist, I need to have age. You have address. I may ask, wow, could you use Oracle Spatial, and could you calculate the distance to the destination? I'd really like to know if I put my new store for selling hybrid coffee, what's the range of people and what the distance is for these individuals, or what's the commute time? I may have call detailed records. I want to know how many dropped calls. Well, SQL patterns is a great tool or technique for that. What % of my calls are international calls? If I have my salary and I just got a salary increase and I'm trying to figure out which employees are likely to leave, maybe I got a 5% increase, but everybody else got a 10% increase. So I really would like to know what's my % versus peers. Again, these are all the types of SQL data transformations you would perhaps be doing, purchases by category. But we as a data scientist, we'd call that creating engineered features. It's sounds a little bit better. They're engineered features. But you're doing that work already, is my contention. So I like this guy, James Taylor and Neil Radon. They came up with a great book here about data preparation. So the wrong way of doing this is to catalog everything you have and decide what's important. The right way is the Albert Einstein way, right? Work to find the problem and then work backward from the solution and look what is the data that I would most want to assemble to solve the problem. So that's week 3. So we've done a certain amount of data preparation. Here's a derived variable, something called recency frequency monetary. So you can read the SQL here. It's a clever little SQL script. I actually got this from Ari Moses, a very clever guy, and I was trying to explain what I was doing. Again, I go back to the database SQL expert, like all of you, I would hope, and I say, hey, here's what I'm trying to do. Could you help me out with that? And I get this little RFM combined score that I want to bring in as a joined variable. So with this data understanding, I'm not, by the way, moving the data. So the data remains in the database, all the encryption, all the security, all the backup is all in play here. So I'm not doing data extraction, I'm not doing data import, I'm doing all the model building inside the database, saving time and money. And most of my customer references say, what used to take me for building machine learning models and operationalize them weeks or months, I can do in immediately, seconds, minutes, hours, because it's just a script, right? It's just all running inside the database. Oops. So now we're up to, where are we? Now we are up to, I'm having a little problem with my system jumping here, but what we're doing here is we're saying, well, you as a database developer, you can bring in more data because you have access to it and you know what the relevant variables are. So rather than a data scientist starting out with, say, 5, 10, or 20 variables and getting this nice green line here and getting a decent model, if you think about going back upstream and thinking about all those other engineered features that you can create, each one of those more intelligently derived variables, um, it increases the model accuracy. They're called engineered features, and that's where your domain knowledge is really key. I contend that that bringing in the right variables is far more valuable, than having the perfect algorithm. A friend of mine was saying, Charlie, we're trying to reduce the amount of no-shows at hospital doctor appointments up in northern New England. What do you think the most powerful variable was? It's a real head slapper. I thought, I don't know, up in the weather, maybe snow. Um, how far is the distance? And he said, nope, the most valuable variable was, have you ever been a no-show before? And as soon as you say it, you go, holy mackerel, that makes so much sense. I, with my domain knowledge, could think about that. I, as a SQL developer, could bring that variable in just like that. And so that is a very, very powerful variable for building a predictive model. So we're up to week 4. Here's where the magic happens. Now, this is pretty straightforward. I'm going to build a model. I'm using what's called here an attribute importance model. So as DBMS predictive analytics explained, there's another way to do this with the attribute importance. This is the most straightforward, the most simplest way, but it's not. There are other ways that you could do this as well. But I just wanted to show it. It can be 1, 2, 3, 4, 5, 6 lines of code. And when you're done with it, it shows you what are the key variables. So all of the algorithms are something like that. They're just a little bit of SQL code to do it. Here we're going to go off and we're going to build a predictive model for who's likely to have good credit. So remember the splitting the data into train and test. Here's a little bit of code that I provide with the sample notebooks that come with the autonomous database. Notice what we're doing here. We're taking a random sample with a 60% sample, and then we're doing the holdout sample. So we've done our splitting of training and testing. We set some parameters for the models. If you're using the graphical user interface, this all happens for you automatically. But this is what we're doing here. Now we execute our model with building a build and then test the classification model. And you can see kind of what we're doing here. So very, very straightforward. We go through this in more time if you have. But my point is, if you can read SQL, you can kind of see what we're doing here. It's not really that complicated. It doesn't have to be to build the model and then test a model. And once you've done this, using the algorithms that we've provided, they handle a variety of different types of techniques. Then you can now apply the model and evaluate the model and see with your randomly selected holdout sample, you can see how well it does. And you can see this is a lift chart and shows the incremental value add that after like 20 or 30% of the population, I've gotten 40 or 50% of the people I'm looking for. So there are different techniques for evaluating the model. We're adding more and more automation, something even called AutoML that does this for you. So there's even more automation coming here. And we provide a lot of examples. So there's one for attribute importance, one for association rules, anomaly detection, and so on. So time series forecasting, each of these different examples are here available for you. And you're nearing the end here. You're at deployment now, right? So in deployment, I want to take my model and just apply it. So I'm doing simple SQL apply scripts that run entirely inside the database and for immediate model deployment. Once I've got my models done, what do I do with all these results? I've just scored it. There's the results in a table. I have my probability of having a good credit customer there. What do? Leave the data in the database and come back and look at that data using something like Oracle Analytics Cloud, Oracle Application Express, build an application, embed it into an application. But that key attribute importance that we were showing before, here's a better visualization of that, frankly, better in other visualization tools here than what we would do in our notebooks. Here's a decision tree where we had all the different profiles of people who are likely to be good or bad credit customers. And here we can see them in a pie chart where the slice of the pie shows the number of people. We can also see the probability, and we can see the detailed rules. So 15% of the people fit this profile. Average, poor, very poor, number of recruiters in LinkedIn, blah, blah, blah. So then the prediction is greater than 3 for the outcome of this particular model. And congratulations, you are now a data scientist. Was that so hard? So that's the whole pitch. That's the messaging. I think it's a very achievable, very attainable evolutionary path for people who are data scientists. And here's one of my favorite customers. This is Ka from Fourth Smart Corporation. He's out of Thailand. He was a BI analyst that was frustrated in how long it took him to get his data out of his database from his DBA, so he taught himself SQL. And then I've been kind of coaching him up a little bit on how to use our algorithms. And he just took those notebooks. He uses the drag and drop GUI with Oracle Data Miner, and now he's doing amazing things. He's a customer presentation at Oracle Open World. You can Google it. You can see what he's been doing with some very good work there. This is the UK National Healthcare Service, 65 million people in the UK that have all that healthcare. Well, all that healthcare data is stored in Exadata, and you can use that to analyze the data, look for fraudulent claims, make predictions for better, healthier outcomes. And they've identified $1 billion in savings, 400 potential savings, 400, which is confirmed fraud, 700 million of additional potential fraud identified, and it's just been an absolutely wonderful story. They went from one data scientist and a DBA into now a department of 10 or 12 data scientists and a DBA, and they've been winning awards. They've been doing great work. So why would Oracle succeed in this? And Larry Ellison said this 2 Oracle worlds ago when he was talking about machine learning. He said, well, because that's where the data is, right? That's where the data is. Where else would you do all this analysis? So that's what it's all about. You have the perfect platform for doing this. And so where should I start as a database developer? There's a lot of tools and resources. The best one I would do is just go to Oracle Machine Learning on OTN. There are a lot of features and functions there and examples and demos. You can always send me an email at charlie.berger@oracle.com. You can use the always free tier of the Oracle Autonomous Database. As I said, I signed up on the escalator up at Moscone. It's very straightforward. And I do want to call your attention to the Oracle Analytics and Data Summit that we're running out in headquarters. It's free to join. It's not free to go to the conference. It's about $300, $400, $500, but it's a 3-day conference. Highly recommend that you consider going there. Go to the website, www.analyticsanddataSummit.org. We also do TechCast. Please sign up. It's free to join the community. And with that, I'll thank you for your time and attention. I wish you the best luck evolving towards becoming a data scientist. If you have a chance, follow me on Twitter. And thank you very much for your time and attention.